gosh! Look at the children. Oh my gosh. So, Sachi and Baji were upstairs, but I called them and they promptly came down. Promptly. Sachi, let's look at the outside before it becomes completely dark. So here we are, snow covered, bit of a winter wonderland situation going on. Look at those icicles. Wow. Little icicles, little snow everywhere. Hi! Snow everywhere. Icicles. Icicles. Hello. Welcome. Welcome to the live. Baji. Baji. All right, I'm gonna share the live. Baji. So I just had some peanut butter and honey sandwiches. Peanut butter and honey. And Baji knew that I'm not gonna share with him, so he went upstairs to regulate his emotions regarding peanut butter. And now he's back down because I called him down to do this live. I just wanted to say hi to everybody. Hello, Baji. And then I'm gonna shower and then I'll be back for our physics live. Baji! Little Baji baby kothay, huh? Where is Baji? Oh my gosh. Baji, you're such a cutie. You're such a cutie. Baji. Such a cutie. Jingdalala. Let's do this. Let's share the live. Hi. Hello. Welcome. Welcome to the live, my friends. Hi, Sharn. Hi, Sharn. How are you? Sharn says, kitty. Yes, indeed. Baji is a kitty. Baji Baba is here in the live with you. Sharn Brown. Look at Baji closing his eyes. Hi, Sharn, says Kitty. Hello, Siddharth says, what is the agenda of the stream? So, right now we're just going to hang out with the kitty cats and catch up with everybody who joins. And then later on, we're going to cover physics topics and do some further hanging out. Beautiful kitty. Hi, Chaco, your little brother. Chaco, your little brother says, beautiful kitty. Thank you so much. Hi. Does that make sense, Siddharth? So Siddharth, if you have been to our previous live streams, you know that we have been covering cosmology and particle astrophysics, but right now we're busy with the kitty cat. Little Baba. With the little Baba. Oh. Hi, Sachi. Hi, Jay. Hi, this one is a Sachi. Oh my God. Hi, Eileen. Hi, Eileen. Hello. Baji, what are you licking? What is it, Baji? This one is Baji. Baji, what you looking at? No, I think he's found a little bit of honey. I cleaned up, but not, there might have been one little particulate of honey left. Look at him! Mr. Baji. Mr. Baji. So, so yeah, that's what's going on. We are just catching up at the moment, but I have been covering particle astrophysics from my own thesis. We made quite a bit of progress last night. I think we'll continue that tonight as well. How is everybody doing and where are you joining from if you're comfortable sharing? We're just doing the shout outs now for everybody who joins and wants to say something. Sachi! Oh my gosh. See, Baji wants attention from Fuji now. He is like, I came down for something, some love, some snacks, something, anything. That's what he is saying, Baji. Oh, little baby boy. So, all right. So how is everybody doing? And are you guys ready for the particle astrophysics to start? Or do you want to see the kitty cats playing? Actually, you know what? We will do a little bit of playing because they need the exercise. Let's see. Particle astrophysics. I didn't even know that subject existed. Well, you will learn much about it if you join this live stream and keep coming back. We go live, you know, most days. And yesterday's live stream, if you want to check it out after today, after this one, we started to cover it in more detail. So let's see, on these live streams, the broad theme is cats and books, and the topics from the books that we cover mainly are physics topics, which is my background. And I've been sick, so I had to be a little bit more sort of saving my voice here. But for the longest time, I think for many live streams, we were covering 20th century physics, modern physics, from the 1900s, including relativity, quantum mechanics, those types of topics, sort of in a popular science communication style. Then we moved on to more recent topics like open questions in the universe, such as dark matter and dark energy, and we were covering more cosmology topics, as well as astrophysics, because dark matter can be approached from a cosmology or astronomy or astrophysics point of view, a little bit different each one. So we talked about that. Then more recently, like over the course of the last few-ish live streams, we have been more focused on particle astrophysics, because I feel like once you've laid down the foundation for particle physics, which has its roots, of course, in quantum mechanics, which we talked about with regard to the 20th century, which is when all the big developments of quantum mechanics happened. You start to get into particle physics closer to the end of the 20th century, and I mentioned about the, few different particle families, all the particle families, broadly just leptons, quarks, and bosons, and that leads us into, learning a little bit more about particle physics. But then when you mix that together with astrophysics, you basically get particle astrophysics. It's a way to learn astronomy and astrophysics using particles other than visible light. So I covered this in a lot of detail yesterday, and I'll continue it today, actually, after I shower. I think right now I want to hang out for a little bit with the kitty cats and you guys, and then I need to like take a shower, and then I will get settled. Because once I start my physics topics, sometimes my lives go on for hours and hours. Like last night, we were live for like over 6 hours. So I'm still answering your particle physics question. That's why it's taking so long. But, or sorry, particle astro question. So, anywho, if you're interested, we have been talking about particle astrophysics, which is basically astronomy and astrophysics utilizing particles that are not just the traditional approach of visible light, but also including other cosmic messengers such as gamma rays, X-rays, which is still light, but not visible light, as well as completely other particles such as cosmic rays, neutrinos, and gravitational waves. So that's the topic that we're covering in the live streams these days. Okay. We also have the kitty cats as part of the live streams. So, whether it's cats or physics or books, you're going to find something interesting here. What degree are you pursuing? I have already finished all my degrees in physics. So I have a bachelor's, master's, and PhD in physics in the subfield of particle astrophysics. Other degrees that I also pursued are in some other subjects, but the ones I finished are the ones that I mentioned just now. I also did a, math minor and all that stuff, but mostly the degrees that I did finish are all in physics. So that's why I cover physics topics. They're all very interesting, especially if you, generally speaking, when people don't pursue physics beyond the undergrad, you might not have kind of seen these subjects or topics too much because you'd have to go to grad school. And I think that's a shame because the more interesting stuff is generally taught after undergrad, after college. So, whoops. It's okay, Fuji. The auto feeder just gave them their automatic food. Here you go. You can share. You can share. Here you go. So, let's see. Hi, Gurjar Harsh. Gurjar Harsh. Number there. Okay. Good morning, USA. Hi, good morning. Hello, Gurjar. What was the equation for which Einstein was asked advice for combining E equals mc squared and photon? So Siddharth, Jen is asking something about what Einstein was asked his advice for. Do you mean during the World War II when they were looking into the atomic bomb? Is that what you mean? Because, Einstein has worked on many things. His biggest contributions depends on which year, but in the year 1905, he worked on, he contributed literature on, so he'd already worked on special theory of relativity, which included the space-time relativity as well as energy mass equivalence. Also, he contributed to photoelectric effect and Brownian motion. After that, in the later years of sort of after 1905, he started working on general theory of relativity. These are what he's mainly known for, the relativity theories, but he got his Nobel Prize for photoelectric effect. A lot of people didn't really understand relativity back in those days, and they were probably trying to give him the Nobel Prize for something a bit of a safer option. So he's also considered to be a godfather of quantum mechanics, the old quantum theory where light is a particle. That's something he also contributed to. And then E equals mc squared, that part, that bit, which plays a role in the atomic bomb, actually was realized by somebody else. But of course, he's the one who had already given us that equation. But the fact that it plays a pivotal role in the atomic bomb was given to us by Lise Meitner, who fled from Germany as a scientist in Germany. She came over to the US during the World War. So, oh, good. Gurjar says, I'm fine. Good. No, for someone's PhD thesis taught in intro lecture in quantum physics. What was the equation? Combining wave nature and particle nature. मैं आपको follow कर दिया Instagram and YouTube. Thank you. YouTube family, nice. Thank you so much. Thank you for following on YouTube and Instagram. Thank you for subscribing, everybody, and liking the live, and welcome to the live. So, wave nature and particle nature. Okay, so, well, Einstein did work on basically special theory of relativity, gave us the updated theory of light and how basically the more insight into electromagnetism. So we already knew that electromagnetism gave us the wave nature of light, and that electromagnetic waves were basically light waves. But people, didn't really understand how electromagnetic waves were waving, how they were coming towards us through space, because they didn't really totally understand the concept of light. The fact that the speed of light is a constant of nature, those types of things were still not properly understood. Okay. Hi, Marilyn. So they did not fully get, because Maxwell, there were people who had worked on electric fields and magnetic fields and understood that they changed into each other, that they were related, and something that was sort of the wave carrying electromagnetic waves, that was basically light. And we basically got this relationship between light and electromagnetism already from Maxwell's equations. But they just did not have the more insight of what it means for light and the speed of light to be a constant of nature. So that's what we get with relativity. All of that stuff with the space-time being relative, the energy-mass equivalence, it actually comes out of the fact that the speed of light is a constant of nature. And getting this math worked out for inertial frames of reference, basically inertial frames, like even if you go at a very high speed, for example, close to the speed of light, you would still experience the speed of light as being the speed of light. So this is a very sort of different insight that Einstein got and gave us his postulates from, that we didn't really have yet. And the relative nature of space-time was something we didn't have yet until that point. Now, of course, the relative nature of space-time did not play a very big role unless you were thinking about these more extreme conditions and speeds that are much higher than our regular speeds of classical life. So those were the reasons why, classical mechanics was working just fine for a long time. Even now it works fine for the most part, but if you want to have the more updated theory for light and gravitation, then you need the special and general theory of relativity. So it provides corrections to the classical mechanics, basically. So that's what that was. And in the intro classes, I believe they teach, this is what they teach. Like they teach, probably modern physics teaches special theory of relativity, not so much general theory of relativity, but modern physics teaches special theory of relativity and the implications of it. So we can look real quick at this book. This is an electromagnetism book from that's used for teaching E&M in undergrad. And yeah, so basically the way physics is taught, generally special theory of relativity is taught as a add-on topic kind of towards the end, so it might not be absorbed very well when it is taught as part of the regular curriculum. And it's because you can avoid special theory of relativity to a large extent when learning about other types of physics like classical mechanics, even E&M, you can go through all of it without special theory of relativity. But it's the more complete theory to evoke to include the special theory of relativity and use the 4-vector type of math, like the 4 space-time type of math, used to calculate wave of a particle derived from energy mass equation and photon energy equation. So the wave equation of a particle, so that's quantum mechanics. So basically, Einstein worked on light, and he gave us the correct theory for light with regard to its wave nature as well as its particle nature. So the special theory gives us light as a wave, how that affects everything, and then photoelectric effect gives us light as a particle. So Einstein worked on the wave-particle nature of light, for sure. But the wave equation, the fact that matter too can have a wave-particle duality, is something that comes from quantum mechanics. So, they all worked, it happened during his time. So it was a contemporary effort during Einstein's time. But the people who worked on, that are slightly different set of people. Oh my God. Baji was using the bathroom I think he has messed with his automatic toilet. Anyway, I'll fix it later. The people who worked on quantum mechanics. So Schrödinger is the one who actually wrote down the wave equation for a particle. So now coming to quantum mechanics, this is the mechanics of the very small. So when you have more classical objects like, yes, de Broglie's equation, got it. Yes. When you have more classical, so de Broglie's equation will give you matter waves, so you got it. So what is your question now? Tensor. What do you mean by tensor? So tensor, are you talking about Einstein's tensor? That is Einstein. So by the way, I have a live stream video on my old live stream tab called something like Einstein's equations. So if you're interested in the Einstein tensor, then you can go and look at that. But basically, let me just finish the story since I'm not really sure what you're asking. Basically, Schrödinger wrote down the wave equation for a particle. Because quantum mechanics is the physics of the small, physics of particles, it's not like classical mechanics can, give us this description of the position as a function of time of various classical objects. But for quantum mechanics, we needed something else. So to formalize those types of things for quantum, Schrödinger wrote down the wave equation for a particle. But then later on, it was kind of problematic the way he wrote it down. And it was someone else in the quantum mechanics camp, Max Born, who said that actually the wave equation of a particle is not giving us the position of the particle, but the probability of finding that particle. So, and that's how the probabilistic nature of quantum mechanics developed, and uncertainty principle developed, and all these very big developments in quantum mechanics started to happen. So this is a different kind of effort than the light having a particle nature. That happened first. So by the time it's like 1905, light having wave and particle duality was already sort of underway. But then quantum mechanics developments took some more time, and people struggled with it a lot. We actually talked about this in detail in a lot of the different live streams where we were covering this. In de Broglie's equation, why do we ignore momentum part of the energy mass equation? I used to have doubt when I studied it. In de Broglie's equation, why do we ignore momentum? I'm not sure I follow that. Maybe I'm looking at your question sort of out of context. We can go through the equations if you like. We should do that in more detail, So I don't know what that, if they ignore momentum. But yeah, okay. I understand that there is some question about the equations. We can certainly review them. So basically, this development of the wave equation representing a probability rather than a certainty about finding the particle was something that a lot of people struggled with and did not like about quantum mechanics. But then it actually all made sense, that because the probability way of looking at it was good, because the wave equation otherwise would have kind of meant that the electron, if the equation is for an electron, that the electron could just keep on going forever and just be somewhere else in the universe, and not close to the nucleus. But when you write it down as a probability of finding the electron, then it makes sense that that's what's being represented with that wave equation. So the wave equations in matter give us the probability of finding the particle, and not just about finding the particle. Let's look at what you might be asking about. De Broglie's equation derivation. We derive it from E equals mc squared, and not E squared we derive it from E equals mc squared, not E squared m squared c to the 4 plus b squared c squared, and E equals h nu. Let me think about that. So, this sounds like a little bit of a simplification. The way I was gonna suggest is basically looking at, but generalize it to all particle. Hey, Steven. So I think we can start it at a more basic level and start with the wave equation of a particle and see where we get. But, in undergrad, the way it's derived might be a little simplified way or something like that. I'm still not entirely sure what they covered in the class. I wasn't there. I wasn't there. I studied quantum mechanics from this book, you know. Well, this is one book. There are many books, but this is Quantum Mechanics by Peebles. This is the undergrad book that we had to use in our physics bachelor's program. And then there is other books in grad. So we can definitely derive this. We should do it. I should get my notes ready for that and go through it in one of the live streams if you're interested. It sounds like there's some question about the derivation of the matter waves, which is valid. That's a great question. I can certainly try to go through it in one of the live streams. Recently, the equations I was going through were for general relativity. They were not for this particular topic, but we certainly, let me see if Griffith does anything with this. So this is Griffith. This is E&M book by David Griffiths. This is also undergrad. I was looking at when you asked about special theory of relativity, I was looking at this. So let's see if there is anything. Steven said, hey all, hi. If there is anything here that we can look at, which you might be asking about. So, so yeah, special theory of relativity, because you mentioned about the E equals mc squared, I'm guessing that the whatever derivation you guys did probably started with special theory of relativity. So that's why I'm looking at this chapter now. Let's just go through it in this book and see if there's anything we can understand. Let's see. Classical mechanics obeys the principle of relativity. The same laws apply in any inertial reference frame. By inertial, I mean that the system is at rest or moving with constant velocity. Okay. It is known that Maxwell's electrodynamics, as usually understood at the present time when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, okay, yeah, no, whatever. Let me read this. So this will be a quick recap of special theory of relativity. The laws of physics. So there's two famous postulates in special theory of relativity, and these are the principle of relativity, which is the laws of physics apply in all inertial reference systems. And number two is the universal speed of light. The speed of light in vacuum is the same for all inertial observers, regardless of the motion of the source. So those are the main things out of which you pretty much get everything. So then I see the equations for space-time, time dilation, length contraction, moving clocks run slow, those types of things. Lorentz contraction. So these should be kind of familiar if you covered all this. Then dimensions perpendicular to the velocity are not contracted. Got it. Good, good, good. So this is all review. And then does he, I don't know if Griffith's structure of space-time. Oh yeah, good. So he does talk about four vectors where time gets the 0th index, basically looks like that. X 0, 1, 2, and 3, and he's putting the index on the superscript, basically, meaning that it's a little bit of a different notation. The relativity type of notation too we covered in my live stream earlier, which is called Einstein's equations, something something. And then we have space-time. Let's see if he's gonna do anything with, oh yeah, okay, so now we have proper relativistic energy and momentum. Okay, good. Oh, there we go. Here's what I think you were asking about. Look at this. I even highlighted it when I was studying this myself. So, in every closed system, the total relativistic energy and momentum are conserved. Relativistic mass, if you care to use that term, is also conserved, but this is equivalent to conservation of energy. Rest mass is not conserved, a fact that has been painfully familiar to everyone since 1945. Though the so-called conversion of mass into energy is really a conversion of rest energy into kinetic energy, note the distinction between an invariant quantity, same value in all inertial systems, and a conserved quantity, same value before and after some process. Mass is invariant but not conserved. Energy is conserved but not invariant. Electric charge, as we shall see, is both conserved and invariant. Velocity is neither conserved nor invariant. I too was about to do bachelor's in physics, but Karan Jani told me you'll end up poor. Who is Karan Jani? So the scalar product of p mu, with mu being in the superscript with itself, is p mu, p mu. Yep. As you, so that you can, in terms of the relativistic energy, it boils down to E squared minus P squared C squared is equal to M squared C to the 4. This result is extremely useful, for it enables you to calculate E if you know P or P. Okay, got it. And then, does he say anything about matter waves? Relativistic kinematics. By the way, you might ask what distinguishes a photon. Yeah, I just want to go through it because it's not a very long chapter. And it's kind of fun to see what I was doing. Okay. Well, if not from here, we will definitely get it from the quantum book. The field tensor. Yay! Oh, God. Let's see. Yeah, we'll go to the index. Oh, man. It could be that he doesn't, just because that it doesn't really, he might not care about it. Yeah, no, I don't see it. It's not there. No, it's not there. Not in this book. Okay, so Griffith's E&M is just kind of special relativity notation and giving us the energy. Basically, special theory of relativity was just the space-time relativity and mass energy equivalence type of stuff, right? So it's not really about matter waves too much. So yes, exactly. So it's more of a quantum thing. So de Broglie, that whole equation thing, that's more of a quantum mechanics thing. It's not a special theory of relativity thing, although there is a connection, of course, but basically, exactly. So Heisenberg uncertainty principle, that's more of a quantum mechanics. That's what I was talking about earlier, which is that you get, after you write down the Schrodinger wave equation, this might not have been how it was taught to, people in other majors, but basically it all starts with writing down the wave equation of a particle by Schrodinger. And then Max Born realized that what he had written down is not the wave equation of the particle, but the probability of finding that particle. And then from that, you actually get uncertainty principle by Heisenberg, because this probability, means that there is some uncertainty, and it's not an uncertainty as in like an error, but uncertainty of nature, of not being able to measure something beyond a certain level. So, and it had some interesting connections with special theory of relativity as well. So it was staying consistent with relativity. So you would have found our discussion interesting when we talked about the debate between Einstein and Niels Bohr. We talked about that for a while. So anyway, coming to this part in this book, this is Quantum Mechanics by Peebles, and we will talk about matter waves now, real quick. So the de Broglie relations. Since light, which clearly exhibits the properties of a wave, interference and all that, can also act like a gas of particles. So it's kind of like there is a connection, right, with Einstein, because he worked on the Bose-Einstein equations as well. And you know how light is a boson, and bosons follow the Bose-Einstein distribution, kind of like a gas of particles. And so all that. Anyway, these things were developing all, kind of simultaneously, right? So sometimes it's hard to remember, like, which topic is this again? But anyway, it's more quantum related, the thing you're asking. Since light, which clearly exhibits the properties of a wave, interference and all that. Oh my God. Oh, you know what? 1 second. 1 second. So I am looking at this book, Peebles. Maybe you have it. I don't know if you have it. Chapter 1, page 26, okay? And so maybe this is the part that you're asking about. So I'll let you just kind of look at this. You know what? Because I need to get a sip of water. I have been sick. So here, let me just show you. I think this is what you're talking about. Is this the part you're talking about? Let me just let you look at that for a second, and I'm gonna go get a water. Oops. Oh my God. It got really cold here suddenly. Okay, yeah, perfect. So then look at this page, that this is sort of where he starts to, or this book starts to cover matter waves. I'll let you just read that for right now. I usually go through it with you, but I need to get some water here. So let me set this up and let you just read that. So looks to me like he's using it's the Planck. It's kind of how we write down energy as Planck's constant times the frequency. Same thing, but for momentum, Planck's constant times well, another way to do it is to just kind of make sure that the units work out. You know what I mean? Momentum is a unit of mass and then speed, right? So it's like it's gonna be a length over time. So whatever it is has to give us time in the denominator. So that's why K is probably a wavelength. Would put the length in the numerator. Hi, Fuji. So the propagation vector in this, so he's starting with these definitions. Psi is e to the I phi, where phi is k dot r minus omega t. So he's writing down basically a plane wave function. The propagation vector in this function is k, the magnitude of k is the wave number, and the angular frequency of the wave is omega. So this is sort of how in physics we define things. The symbols and notations might be a little different in a different class, but basically remember how I was saying that it all starts with writing it down as a wave function. So since light, which clearly exhibits the properties of a wave, can also act like a gas of particles, as discussed, one might guess that material particles exhibit wave properties. The connection between the energy and momentum of a particle, like an electron, and the frequency and wavelength of the wave associated with the particle was introduced by de Broglie. So first things first, you're going to have to start with a plane wave function. So this is given by, this is the wave function. It's going to be something like this e to the I phi. Basically, you're writing it down in a complex number form. And what's in that phi, that phase, is basically kr minus omega t. And k is the propagation vector of this. It's kind of like how, one second, I gotta turn the tap off. Whoops. Okay, let's see. I'm trying to see if are you familiar with how plane wave functions are written down? Sort of, it's done a lot in E&M. So the propagation vector in this function is k. So k is a vector, but the magnitude of k is a wave number. So because this k is dotted with r, and you know that the overall quantity is a phase, you know that it has to be unitless. So that's why it's a wave number, as in it's going to have the dimension of length in the denominator, and it's dotted with r, which has the unit of length. So together it will be unitless. And then omega and t are the same thing. Omega is angular frequency with time unit in the denominator, so it'll cancel out with the t time unit. So overall, this phi quantity is going to be the phase of the wave, and it's going to be dimensionless. Okay, this is basically the structure of writing down a plane wave function, and that is how we start to write down the wave function even for a particle. And this is very common way of writing down a plane wave function. It's all over the place in, say, E&M and things like that too, or even classical. So basically, a plane wave function is given in this form, the psi e to the I phi, and then the phi is given in this form. So now let's see what else he says. Basically, propagation vector in this function is k, the magnitude of k is wave number, angular frequency of the wave is omega. This is a very common way, at least in physics, to write things down, okay? An example is the pressure wave discussed, whatever. We will assume that here that omega depends on the magnitude of k alone. The function omega is going to be a function of k, is also called the dispersion relation. Okay, that's a detail. As indicated in right here. So, oh, by the way, this is what's going on with that phi. So k is the propagation vector. This is the direction in which the wave is propagating. Okay, and all the other things are in this picture as well. The propagation vector for a plane wave is k. Now, you might have seen it as a different symbol in your class, but here the k vector is the propagation vector. This is the direction in which the wave is actually going. You know how in E&M, basically, if your electric field could be, going vertical to actually where your wave is traveling. Like we call electromagnetic waves transverse waves, right? So what that means is that something that's actually oscillating is not the same direction in which the wave is going, right? So that's just another example of a wave and how to write down a wave. But basically, it's important to understand that the propagation vector is going to have the same direction as it means that's the direction in which the wave is propagating. The propagation vector for a plane wave is k. The positions r that lie in a plane of constant phase at a given instant of time will satisfy r dot k is equal to a constant. The plane of constant phase is normal to the propagation vector k. So that's what I was saying just now. The plane of constant phase is normal, meaning perpendicular. So it's kind of like how in light, the electric field, of course, it depends on, are you familiar with electromagnetic waves? Basically, in electromagnetic waves, the E and the electric field and the magnetic field are perpendicular to each other, and then light is perpendicular to that. The propagation of the wave is perpendicular to all of that. So it's not the case that the same plane in which something is oscillating is also the plane in which the wave is propagating. So that's yeah, got it. Okay. So the plane of constant phase is normal to the propagation vector k, meaning that the plane of constant phase is perpendicular. So this is that plane of constant phase, and it is perpendicular to the propagation vector. So you were asking what the propagation vector is. That's what this is. Two planes of constant phase with phase difference 2 pi are separated by the wavelength lambda equal to 2 pi over k. So that's why that k, remember, is also a wave number. When you take the magnitude of the propagation vector, you should be getting a wave number. So this is just a way of writing down the plane wave function. Once you write this down a lot for a lot of different types of things, like this plane wave function, you could almost write this down for anything, like it's a simple plane wave function where the definitions of the different things are as follows. K is the propagation vector. It's perpendicular to these planes of constant phase, and the relationship. So I mentioned earlier that the total phase is given by k dot r minus omega t. See how the phase of this plane is phi, but the phase of this one is plus 2 pi. So basically, it's almost like this phi can be shifted as plus 2 pi, and then you would keep on getting the same thing. Because, it's kind of like the sine and cosine, but in the complex function way of writing them, in other words. So that's what this e to the I phi really is. There's another way of writing e to the I phi, right? If you're familiar with the complex wave functions. Perfect. Okay. So anyway, as indicated, so they're looking at, that's what this is. The distance between planes with phi differing by 2 pi, we already talked about that. A surface of fixed phase advances along the direction of k at the phase velocity. So phase velocity is going to be given by Vp omega over k. As one sees by considering the displacement delta r, that would balance the time shift delta t to hold phi in equation. They're explaining wave y. Oh, I don't know. That's how we're going to get to the next part. They're just kind of going through this, how to get the de Broglie relations, basically. So are you asking why they wrote down a wave equation? So we're starting with a wave equation because we are hypothesizing that matter too will have a wave nature, and so we start by writing down a wave equation for it, and we define out how to, it's a mathematics basically. We want to define out this wave equation, write it down, and also define out what are the different parts of it, like the k, what does it mean, the lambda, all that. So then we saw in section 2 that the dispersion relation for a photon is omega equal to kc. According to the Planck relation, the photon has energy of E equal to h bar omega. So we know also from photoelectric effect that the photon has energy of h bar omega. So that's like Planck's constant times angular frequency. And we knew that the energy of a photon is proportional to its frequency, right? And in this case, we're writing it down as an angular frequency. So anyway, photon has momentum of E over c, so that's going to be h bar k. So a photon doesn't have any mass, right? So its p, or momentum, is E over c, or h bar times k, which is the wave number. These are just different ways of writing down the same thing. De Broglie proposed that electrons may exhibit the same wave-particle duality with the same de Broglie relations between energy and frequency and momentum and propagation vector. E equals h bar omega, which is the same thing that we wrote down for photons, and P equals h bar k. So then we're basically writing it down now with, in terms of lambda, that's going to be 2 pi over k, h over p. This is equivalent to the second of the de Broglie relations. The de Broglie momentum relation offers a way to understand the Bohr-Ehrenfest angular momentum condition in equation 4.5. Where is 4.5? Equation, oh, you know what? This is going to be, oh yeah, okay. This is angular momentum of the electron in orbit around the proton in a hydrogen atom. This is going to be L equals N times H bar, where N is 1, 2, and 3. Got it. So it's kind of like the orbital, let us imagine the electron with charge E is moving in a circular orbit. Okay, whatever. It's a simplification, but it's fine. So anyway, next we want the wave to be continuous, so there has to be an integral number n of wavelengths around the circumference of the circle. 2 pi a. Okay. A non-relativistic particle of mass m moving with momentum p has kinetic energy p squared over 2m, thus the dispersion relation derived from the de Broglie relations is, so I think they're putting together the equation from the photon, which was this, which was this, and the fact that now there is a mass because we have a non-relativistic particle of mass m, so you can do the math to figure out how omega is now related to the mass. The phase velocity in this case is p over 2m. This differs from the usual relation between momentum and velocity by a factor of 2. However, as we will now discuss, that is because we need another measure for the velocity. So we have group velocity of a wave packet next. So this is how de Broglie assumed that the plane waves can be superimposed to get more general wave functions. So here is how that's written, psi of r and t, because it's going to be, this wave equation is going to be a function of both position and time. And then, so you get that, and then, yeah. Lastly, you get this. After all that group velocity math, you get this, p over m. So I think de Broglie was literally writing down the equations for a photon and then saying that I'm just going to assume that that matter waves have the same thing and write it down for the matter waves. But the more, I would say, the more correct, like, see how Schrodinger's equation is next. After we covered this de Broglie matter wave stuff, the next part is Schrodinger's equation, single particle wave equation. This is what I was talking about, which is where Schrodinger writes down the wave equation and its partial differential equations. Schrodinger in 1926 wrote down the differential equation satisfied by the matter wave associated with a non-relativistic particle moving in a potential well. He was guided by an analogy Hamilton had noted between the motion of a particle in classical mechanics and the short wavelength limit of the motion of a particle wave in a medium with index of refraction that is a function of position. So according to de Broglie's relation, E equals h bar omega, that means that the matter wave associated with the atom can only oscillate at discrete frequencies. One gets discrete frequencies from the solutions to a wave equation with fixed boundary conditions, as we saw in the normal mode analyses. Thus, a theory for the discrete energies might be based on a wave equation. By de Broglie's relations, a wave with energy E oscillates with a frequency of omega and goes like that. the wave function therefore satisfies the differential equation of this I h bar d psi dt. So now we're taking a partial derivative of that. If the wave has momentum of p, de Broglie's relations say it has a wave number of p over h bar. That means the wave function varies with position as. Okay. So I think basically de Broglie was guessing that matter waves will do something similar, and you can just write it down and see what you get. And I think he got pretty close because the discrete nature kind of goes hand in hand with the fact that, you know, depending on which orbital your electron is in around the nucleus, you get a different energy, right? So there is sort of a discreteness to that, which is nice. But the more general way of writing it down is going to be the partial differential equations way, the wave equation way of writing down for a particle. And then there's some further math to, first of all, I think Schrodinger did it for non-relativistic matter. Then I believe it was, who did it? Wait a minute. Schrodinger wrote it down, and then somebody else did it for relativistic. It might have been, I forget exactly who wrote it down. No, it's going to come to me. Oh, Dirac. Dirac did. Okay. So Schrodinger, yes. Yeah, they all got Nobel Prizes. So Schrodinger wrote down the wave equation for a particle using sort of the potential well way of writing it down, right? Then Dirac wrote it down. He included relativity. So he turned these equations from Schrodinger for the wave equation of a particle into relativistic wave equation for a particle. And then it started to have problems later on when people realized, oh my God, the wave equation is kind of like putting the electron anywhere in the universe. So then Max Born said that actually it is the probability of finding the electron, not the electron. So that's how it kind of progressed. So if you really want to understand these equations, I would start with the wave equation. You could write it down as a non-relativistic wave equation, like this, you know. And it's you could do it the simple way, like what we were looking at earlier. This is cool. This is pretty cool. The more general time dependent. So yeah, see, there's always a little bit more that you can do, right? Which is always interesting. A particle in a potential well, such as an electron in a hydrogen atom, has a potential energy V of R. So even if you write down the potential energy, it's not like that potential energy is going to be a constant, right? That's going to be like a function of the position, so R, as well as kinetic energy. Schrodinger generalized the wave equation for the case of a particle with energy E and potential energy V of R by adding the potential energy to the kinetic energy. So this E that was over there is now over here as well. And we've added the potential energy now. So this is very important because with this, you can actually now start to do more. Like I was saying how quantum mechanics is like, you want to write down the position of you want to write down the position of a particle as a function of time. That's really what we're doing. Like that's basically what physics is. It's like figuring out how to write down the mechanics of something, position as a function of time, for example. But for that, you have to have all the terms in place. You could just say E, like right here, but really in the case of, for example, an electron in a hydrogen atom, that particular scenario has the potential energy V of R, right? So anyway, whatever. It's almost like it's in a potential well, right? And it can go up and down, basically. Like it can go farther away from the nucleus and be in a more excited state, or it can be more in a ground state, right? Like sort of the orbital Like n can be 0, 1, 2, 3, 4. You know what I mean? Like that. So now he's writing down like this: minus h bar squared over 2m, second derivative of psi, plus v of r psi. Now, applying this equation twice and recalling that the kinetic energy is p squared over 2m, one might guess that the wave equation for a free particle, lol, that's funny. Oh my god, right. P squared over 2m, yeah. That's funny. One might guess. So they were guessing, you know, back in the day. Particle in a position. So anyway, then you get this. And then this is Schrodinger's equation for a single particle with definite energy E. The more general time dependent. So if you know the energy is E, then this would be it. But the more general time dependent Schrodinger equation is obtained by eliminating E and putting in this. We arrived, wait a minute, I thought we'd already done that. I h bar, partial psi, partial t. Okay. We arrived at this equation in which the system has a definite energy E, so we are removing E and calling it this potential well. We will assume that the more general solutions to this equation where psi does not vary with time as e to the minus I et over h bar also are allowed. Thus has the interesting consequence that Schrodinger was reluctant to accept that in states represented by such solutions, the system does not have a definite energy. So Schrodinger was upset by this himself, but that was the reality. It is customary to write equation 6.7, which is this big equation. So in this big equation, all of that stuff is called H. Basically, we boil it down to H, or the Hamiltonian, for the time-dependent case, and when the energy is known, then we call it E. So H of psi, it's almost like this operator. It's a derivative operator on the wave equation, and when you know the energy that the electron is in, then it's almost like that's the solution of it, so you call it E psi. So here H is the derivative operator. All of that stuff is H. It's understood that the wave function for the system is of the form psi of r e to the minus I et over h bar. E is energy. It's that constant energy case where psi of r is a time-dependent solution. This requires that V be a function of position alone. When V varies with time, energy is not conserved, and one must use the more general equation. Like this one. This one assumes that obviously potential energy is changing with position alone. The Schrodinger differential equation has to be supplemented with boundary conditions. For a bounded system like a hydrogen atom, it is reasonable to require that the psi wave be bounded too. That is that psi go to 0 at large distance from the proton. So, right. Basically, if you just write down this, then it looks like this is where it will be helpful to look at it as the probability. So we'll talk about that later. But basically, this is where this boundary stuff that they're talking about is to help it help this H psi equal to E psi thing actually realize what is the case with an electron. The electron doesn't just go infinitely into space or something, right? It stays pretty close to the proton in most cases, or in the atom at least. For a bounded system like a hydrogen atom, it's reasonable to require that the psi wave be bounded too. So psi should go to 0 at large distance from the proton. This will be formalized in section 8 in the condition that the wave function psi for a physical system be square integrable, that the integral of psi squared over all space be finite. So this is actually the one, I believe this was Max Born who said that this thing is really the probability of finding the electron, and that psi squared is going to give us the probability. So the fact that these wave equations are actually giving us a probability and not the certain position of a particle, this was a further step that people had to take that Schrodinger didn't even like, even though he's the one who's written down these equations. But he actually really did not like the fact that this was ultimately going to be a probabilistic mechanics. The expression in 610, so the Hamiltonian here, is called an operator, because I call it a Hamiltonian. Oh, thank God. Yeah, it is a Hamiltonian. The expression in equation 610, which is the minus h bar squared over 2m delta squared plus v of r, that's called a Hamiltonian for reasons that will become clear in sections 14 and 19. Oh my God. Some other jargon might be mentioned. Equation 6-9, which is the h psi equal to e psi. That is the eigenvalue equation. So E is basically considered an eigenvalue, like a solution to the equation. The solutions psi that are square integrable are the eigenfunctions of the operator h, and the constant E is the eigenvalue belonging to the eigenfunction psi. So in the linear algebra, so all of this is kind of like linear algebra in the mathematics world. So in mathematics, there's these things, eigenvalues, eigenfunctions, and you can get solutions to your eigenfunctions, which are going to be like eigenvalues. So in that linear algebra type of notation, all of this quantum mechanics is basically linear algebra. So in that sense, the E, or the energy, if you knew your particular E that you're in because you know which orbital you're in, that's going to become an eigenvalue. And what you are in, your wave function, is basically the eigenfunction. So the solutions psi that are square integrable are the eigenfunctions of the operator h, and the constant E is the eigenvalue belonging to the eigenfunction psi. The prefix eigen refers to the result that the energy eigenvalues E for a bounded system are discrete. So this is all happening because of the bounded system. And we know it's bounded because there is the V of R. Basically, when you write down V of R as in a potential well, it implies that you're going to be bounded, right? Schrodinger's guess has proved to be remarkably successful. Equation 6-8, which is the IH bar d psi dt is equal to H psi. That equation still is the basic dynamical equation of quantum physics. Before developing the formalism any further, let us look at two applications: the ground state energy of a hydrogen atom to see that Schrodinger can do as well as Bohr, oh my God, and the energy levels of a one-dimensional simple harmonic oscillator to see that Schrodinger can do as well as Planck. Oh my God. So all these people were working sort of together, right? Like some people were more senior than others, but like Planck, I think, is older, I believe. Then it's like Schrodinger and Bohr might be like similar age or whatever. But these people were all working on similar things together: Bohr, Schrodinger, Planck, later on Heisenberg. And they might have been coming to De Broglie, they might have been coming to the same thing in different approaches. And basically, they all merge together at some point. So Bohr has some stuff, particularly for the hydrogen atom. And so if Bohr had done some stuff for the hydrogen atom, like written down some ways of defining out the hydrogen atom's dynamics, the electron of the hydrogen atom's dynamics, say it better agree with whatever Schrodinger just said, right? So that's what the author is talking about. So they're going to prove that out next. But basically, I would say that because pretty much I think it's understood that the Schrodinger wave equation is a good place to start. That's how you write down the wave equation for a particle. And it's nice because you can even define out this potential well. And because you give it a potential well, it works whether you're writing it down for an atom or just in general, right? Because Planck gave us, that Planck's constant, like the discreteness of basically these energy levels and stuff like that. Basically, if you have a potential well in your energy operator, in your Hamiltonian, basically in the Hamiltonian, which is what Schrodinger had, then and you can keep it simple. At this point, the potential well is just a function of position. But it should pretty much work whether it's a particle within an atom or a particle within some other field. So that's the nice thing. So if we're going to be doing mechanics of the small or physics of the small or quantum mechanics, it's basically the whole point is to write down the position as a function of time, or to have some way of describing the motion of the particle, whether that is a particle inside an atom or somewhere else. And I think the good place to start is just Schrodinger's wave equation, and then realizing that it's a probability, and then swallowing that probability is fine. You're getting a probabilistic answer, not a definite answer. And then realizing Heisenberg gives you the uncertainty measure, basically. And then that's it. End of story. So I think, but what De Broglie was doing was basically like a copy paste of like taking photon stuff and special relativity, because that describes photons really well, obviously, and saying that matter waves will do the exact same thing, and here it is. And that wasn't bad. Like, it's not a bad guess, because there was so much being done at that time for matter wave duality, to basically copy paste the equations for a photon to matter and include mass is not a bad way to start the effort. Why is Edward Witten such a big deal? Does he have anything to say something different on the foundational concept? Edward, remind me who the frick that is. I mean, I feel like I've heard this name, but what did he do? Is he a big deal? I don't know. I think Schrodinger is a big deal. He gave us the general wave equation for a particle. Dirac is a big deal. He made them relativistic. Max Born is a big deal because he realized that the Schrodinger wave equation is actually a probability. Max Born, I already said. Heisenberg is a big deal because he gave us the uncertainty principle. Realized that that's a nature thing, not an error thing. Bohr is a big deal. Niels Bohr. He debated Einstein on this whole topic and won, and also did a bunch of work for the hydrogen atom. Who is Edward Witten? YouTube, there are clips of physicists saying they fear him. Oh, okay. I mean, physicists can be pretty scary people. They can argue endlessly. That might be why. Honestly, I have to look him up. I actually don't know. Hey Google, who is Edward Witten?
According to Wikipedia, Edward Witten is an American theoretical physicist known for his contributions to string theory, topological quantum field theory, and various areas of mathematics. He is a professor emeritus in the School of Natural Sciences at the Institute for Advanced Study in Princeton.
Oh, so he does string theory. Oh, that's right. Okay, somebody else brought him up when I was talking about the 20th century stuff, I think. Sure, yeah, no worries. So Edward Witten does string theory. Oh my God. I mean, that tells me everything. Perfect. I mean, good for him. String theory, the problem with string theory is that it is not testable. So I think Edward Witten is probably a great mathematician who probably has great insights, but he's not more famous because string theory as a whole suffers from this problem of not being able to be tested. And in physics, generally, you need experimental evidence in order to say that a thing is a thing. So that's where string theory really suffers. And string theory was, by the way, so in our discussion, we covered this. String theory is basically after all the relativity stuff happened and quantum mechanics saw a lot of progress in the 20th century, and electromagnetism, of course, had a whole new insight after relativity came to be, Einstein and others were actually trying to work on something called the grand unification theory, because a lot of people, even the ones who contributed to quantum mechanics, didn't really like quantum mechanics. They thought it was bizarre and weird. So they were trying to look for a more general theory called the grand unification theory that would unify and give us a more general theory that kind of encompasses quantum mechanics, relativity, gravitation, everything, right? The theory of everything. And then afterwards, this a little bit of a flavor of string theory was already coming out during Einstein's time. Like we talked about the Kaluza, what's his face? Kaluza, some other guy. There were some sort of baby string theory type of things happening during Einstein's time. Basically, this point of like maybe there are more dimensions and we just don't experience those dimensions because they're small or something for us. So basically, there were people, Kaluza Klein, I think it was Kaluza and Klein were two people who basically took Einstein's general relativity equations and showed that you can like solve them more exactly with more higher dimensions and stuff like that, and that would work out. And so then they were like, okay, maybe there are more dimensions. We only experience 4 dimensions, which is the 3 spatial and 1 time dimension. And that leads to sort of all this good stuff, but we don't really have unification. So the grand unified theory was incomplete. But as far as candidates for the grand unification theory goes, string theory or superstring theory later on, it took another 60 years. Like after Einstein's general relativity, some baby string theory stuff was coming out already. Like people were already onto it in the sense of like this thought that you might just need more dimensions and then you'll have it, right? But they kind of abandoned it a little bit because you couldn't test this sort of stuff, right? And also the World War happened and people got really distracted and everybody worked on the atomic bomb and all that stuff, right? And then quantum mechanics kept on succeeding. That's the other thing. Why is someone going to work on string theory if you can find another new particle, right? So some critics of quantum and particle physics actually said that these things kept on growing and growing and succeeding, and so nobody really cared anymore about string theory. And particle physics became a thing because quantum mechanics was so successful. Like particle physics comes from quantum mechanics, right? The fact that quantum mechanics developed so much in the 20th century and kept on succeeding, as in whatever they were saying, they were also able to show with evidence. Like the hydrogen atom, those types of things were happening. Like they were not just, the nucleus was actually discovered, the neutron was discovered. Like these things weren't just math. So that made well, as far as we know, as far as we know, everything experiences just the 4 dimensions of space and time. The reason for including higher dimensions would be to do Einstein's general relativity with more dimensions because that would be allowed, and also to try and explain things more generally. So string theory is a candidate for the grand unification theory, where everything is a string and all these different particles in particle physics is like the mode of a string or something. I'm not an expert on string theory, but basically it tries to generalize relativity and quantum mechanics. So as far as I know, string theory is like the only one that can generalize relativity and quantum mechanics. But it's very difficult. I don't think that string theory, I don't know that it has encapsulated everything that there is in quantum mechanics, because quantum mechanics also progressed very fast. And not only is it sort of a theory and math, like we were just now looking at these equations, right? But it's not just that. It's also the experimental evidence of quantum mechanics was also there. We also experienced it and tested it and everything like that. So we saw the evidence of it. We started to discover more particles. So particle physics became a whole thing. Standard model of particle physics developed, right? Lots of progress happened in the real life for quantum mechanics and particle physics, whereas not much progress happened in string theory, which is why string theory is done less now. It's much less mainstream, and it's just not as pursued by most people. So if Edward is a good guy for string theory, that's great. I mean, somebody should be doing string theory, because I do feel bad that the field kind of got left behind just because they suffer from this thing where they can't really experimentally show anything, because they deal with like 11, I think it's like 11 dimensions, right? And so how are you gonna test that? So that's the issue of string theory. Unfortunately, I think it's very unfortunate, because just because it cannot be tested doesn't mean that there is not a merit to it, but it's been largely left behind by most people because it cannot be tested. But generally, string theory, okay, so now coming to string theory, not that I'm an expert, but it starts with relativity, right? So those people are really good at math and really good at general relativity. So this Edward guy, he probably really knows general relativity. So I'm mentioning this because not everybody does. A lot of people don't really understand general relativity because they don't have to apply it in their type of physics or their day-to-day life. But string theorists do. So good guy for that, I would say. You know, I didn't know that he was that famous, probably because he does string theory, which is not tested, which makes it less successful. But he's probably a really good guy for math. I mean, I don't really know him, but he's probably really good for math and GR. So good, great. And people fear him. Well, that's, I don't think people should fear people. That's not really a good, I don't know if that helps anything. If anything, string theorists should probably make themselves a little bit more accessible and approachable if they want more people to understand what is it that they do, because if people will fear you, then how are you going to ever make any progress? There is no concept of distance for light. How many? Distance for light. Well, light has a finite speed, and it does take it some time to go a certain distance. Is that what you're asking? He is one field medal. You're right. Yeah, for math, that makes sense. Yeah. Yeah, he's probably a great guy. I mean, honestly, string theorists, they have to do a lot of math. So I appreciate them a lot. In fact, everything is good for something, right? So like if I had to learn, say, general relativity all over again, and even the first time when I was taught it was by a string theorist. They're the best at general relativity. They have to start, that's their starting point. They basically take Einstein's equations, which are very complicated, pretty much, and solve them for like 11 freaking dimensions or something. That's not easy to do. That's very hard. So, like we were looking at the math for Einstein's tensor, and the left-hand side was Ricci tensor, and the Ricci scalar, and then the right-hand side was the 8 pi g. I think it was 8 pi g over maybe 2 pi, don't quote me, but something with 8 pi g, and then the energy momentum tensor, right? So I guess so. I guess the string theory tensors would probably have, they would probably be 11 by 11. So we were looking at these 4 by 4 tensors the other day. Um, and the first, so we looked at a little bit of notation too, by the way. Like, so if you're interested in the math setup of general relativity, I recommend that live stream that I already did in the past. It's called like Einstein's equation something, not too long ago. And so over there, we looked at how we had these 4 by 4 matrices or 4 by 4 tensors. And the first index was given to time, right? And we also looked at like notation. Einstein used a bit of a shorthand notation, you know, superscripts, subscripts, they mean different things, and repeating indices meant that you sum over them, stuff like that. So we covered all that. And we set up the basic equations for general relativity or GR. And so you can look at that, and you can kind of even try to do it for 11 dimensions if you like. And that will be more closer to like this, what the string theorists have to do. So I mean, a lot of respect for people who actually do the math for that. You know, they're really good at math. So, and they might even have contributed something unique. Like, so the other thing is, because the math is so hard, a lot of people don't actually know how to solve the equations exactly, right? So if you do solve them exactly, you might actually chance upon some new thing that other people just didn't find because they couldn't do the math. So it's just a mathematical blockage, you know? So string theorists, because they're good at math, they probably have done things and found more things just by doing that. So good for them and us that there are people who do this, you know? And like I said, the reward can be less in doing string theory because it's not testable. I think it gets like less funding now, and people don't take it as seriously. And you're not, if you go through your whole life knowing that the thing you're doing will never be confirmed, that can be kind of sad, right? So more power to the string theorists, but also more power to quantum and particle. These things are good too. I know string theorists probably hate on particle physics just because they got so much more attention lately. For someone traveling at speed of light, do they experience distance? Yeah, of course. So it still takes light a finite amount of time to go a certain distance. So if that's what you're asking, distance is still a thing for light, but nobody travels at the speed of light other than light. Even neutrinos, relativistic neutrinos, neutrinos I mentioned because they're low mass particles. Even if a neutrino was going very fast, it would still be going at a speed less than the speed of light. And it could still be relativistic, meaning that its speed is, something high enough where we would have to do its math with relativity, not without relativity, because relativity really kicks in when you are going at those very high speeds. Then you can't just do Newtonian mechanics. You need the corrections from relativity. So say, for example, I was covering particle astrophysics yesterday from my own thesis, and I was mentioning about relativistic neutrino hitting a quark in the Antarctic ice, and that's how we detect it and all that stuff, right? That's how we try to detect it. So relativistic neutrino would still not go as fast as the speed of light in vacuum. I mentioned how after the neutrino, say from a exotic, high energy event, hits the quark in the ice, it creates a particle shower, and then that particle shower goes at a speed that is more than the speed of light in that medium, producing Cherenkov radiation, but it's still not the speed of light in vacuum. So the speed of light in vacuum is still greater, and only light goes at that speed, okay? Nothing else. Yes, I know. First, they were suspended to travel at speed of light. Suspected, yes. Yeah, exactly. So at first we thought neutrinos were so low mass, we thought that they might be like no mass, but they're just low mass. They're not no mass. So they still have a little bit of mass, and there's like three different flavors. They're definitely more odd and more unique type of particles. And so they were a point of like, they were elusive, they still are elusive, and they were confusing. And they were actually a candidate for dark matter as well. We talked about that too during one of our live streams. Not one, many of our live streams, because we've been talking more about dark energy, dark matter lately. And basically, neutrinos are so introverted, so different, and they only interact through the weak and through the weak force, through the W and Z bosons. So they're so different, and sort of how they have evolved, or evolved as in how they went through the steps in the universe, is also kind of different, because we also have been talking about the evolution of the universe and how, in the beginning it was radiation dominated, and like the photons and electrons and positrons were all hitting each other constantly, and then neutrinos kind of detached, all that stuff, right? So neutrinos are gonna be different. How to physicists explain tensor? So tensor is just a container. So like we mentioned during the Einstein equation live, that a scalar is basically a very simple tensor. I think it's called a zeroth order tensor. Actually, I have a note on this. Let me just read my note on this. A tensor is a generalized math object that represents a multilinear relationship between vectors, essentially acting as a container for data in multiple dimensions, which can be thought of as an array of numbers that describes a physical property requiring multiple directions to fully characterize it. A scalar is a zeroth order or zero rank tensor, and a vector is a first rank tensor with higher ranks representing more complex relationships between directions. So definitely for space-time being a four as in the number four. F-O-U-R, four space-time, right, is what we say for relativity. Basically, that's not the same as the Cartesian, like XYZ math that we generally do. So why this general relativity math is harder is because we are actually in a different kind of coordinate system, because even having just one extra dimension, which is the dimension of time, can actually complicate things, and you need like this metric thing defined out. G mu nu is the metric, which gives you the invariant in a four space time. So that's where tensors come in physics. And for me, I mean, it's just a matrix. It's just a way to, because there's like all these different directions going on, all this multi-direction type of stuff going on. So it's not a simple equation is not going to be able to write down what I'm trying to write down. That's how I think of it. And so I need a tensor now to like write down what I want to write down, because there's like 4 dimensions, and I have to write something down connecting all these different things and parts. But it's not too bad, because 4 dimension and the first dimension being time is still like, it's not the worst thing in the world, because once Ricci tensor and stuff brings in the scale factor. Energy momentum tensor is not something that's too awful, because we've kind of seen it in special theory of relativity. And then there's Einstein's tensor. So, and it all kind of comes together. So that this is what we stepped through in that live that I talked about. And so it's not too bad, but it is something to understand that it's kind of different. It's not like when we do math and physics in Cartesian coordinates with XYZ and we're done, because we understand that very well. But since we don't generally do math with 4 dimensions for mechanics, it's kind of different. So anyway, but yeah, that's to me that's why we need a tensor in relativity. Just kind of need a matrix way of writing things down. Yeah, but tensors are obviously a mathematical object too, right? So in physics, how we look at things is kind of different. The people who are mathematicians, math has a lot of formalization just in general. Like, hi Fuji. Math, like to a mathematician, everything I just said is not a big deal probably because like there's no physical reason for like a coordinate system to only have 3 dimensions, right? So like Cartesian coordinate system is a very common one, x, y, z. But it's also a common one because we live in that. Generally speaking, we don't consider time as a 4th dimension. We consider basically position as long in classical mechanics, as long as you have position as a function of time. Like if somebody wrote down the equation for the moon as a function of time, they could probably predict the position of the moon like 1,000 years later, right? That's how classical mechanics works. That's where it's so different from quantum, because quantum doesn't even give you deterministically where an electron will be 2 seconds later. It'll give you a probability of finding the electron. So people hated that. So that's one difference between classical and quantum. And the second thing is that in relativity, we don't really have it in the same way. It's not, time is part of the fabric of space-time, so it's not separate. So time itself is relative. So the equations are done kind of differently. There is the time that's part of space-time, and then there is maybe cosmic time, so those types of definitions need to be defined out, and the math needs to be set up in a different way. But that's all it is. So for a mathematician who doesn't necessarily do things because of a physical reason, because physics is sort of the way to describe our physical world and physical universe. So things having a physical reason is important. But in mathematics, what's the reason for having only 3 dimensions? They can have 20,000 dimensions if they want, right? So string theorists, when they have like 11 dimensions or whatever they have, that's not a big deal for them. That's normal. So tensors, lots of dimensions, they can do the math for that because they're not trying to necessarily do physics. So string theory is, considered more of a math thing probably in that sense than it is a physics thing. But it is a physics thing too. So, I don't have any problem with it. But it's it's where the math, even Einstein kind of struggled with math, right? Because math is not our main motivation in physics. Math is the main motivation in math. Everywhere else, we consider it a tool, not the main motivation. We just say tensor is generalization of matrix to more dimensions. Oh yeah, okay, yeah, there you go. Yeah, that works too. That makes sense. So did you do computer engineering so that you can be more rich? That makes sense. I think a lot of people go for computer sciences or some other type of thing and not the pure sciences, physics, chemistry. But yeah, that's the point. Oh, Suji is so playful right now. But AI is now knocking on door. Well, there's always, the thing with, anything is that there's always more things to learn and do. AI is basically like statistics, right? So it's like math and data and statistics. So Again, I think the math people will be very happy because I believe that they should be more than comfortable with AI because it's just a bunch of data and a bunch of statistics. So, and statistical models and things like that. So, yeah, that's the nice thing about math. You can apply it to anything. So I like to be a student of math and physics. You know, the thing about physics is that learning new things and relearning and thinking and being sort of like interested in a fundamental understanding of things is very normal in physics. And so it doesn't really matter. We believe that pretty much we probably have to learn something new all the time. You did your bachelor's from US only? Yes, I did my bachelor's also in the US. Hi, Sachi. I did. It was a long time ago. So I am relearning all these equations and stuff now with you guys. I love talking about physics and, discussing physics topics. And then so I got back into it. I got out all my books and textbooks and I've been learning it and talking about it again with you guys on the lives. It's been nice to revisit these topics. But yeah, physics is really fun. Wow, it's almost 5 in India. I should probably sign off. Okay, have a good night. Thank you, everybody. Have a good night. I need to take a shower. So that's great that you asked all the questions, and that got me looking at the quantum book and reminding myself of how that particular topic is discussed. Because I kind of discussed quantum mechanics in a history of science or history of physics type of way in my previous live streams, but we didn't look at the equations in too much detail at that time. And I think at that time, people were still kind of figuring it out with what was even going on during these lives. And so it's probably a good thing. We didn't delve too much into the details, but it's good to look at it more concretely like we did today. So we might continue that going forward. And it was a good review for me as well. Thank you everybody so much for your patience during this live stream and for sticking around. If you're seeing this as a video upload later on, thank you so much for watching, and let us know in the comments what you thought, and let me know any questions. Pretty much as you saw, with your questions, I can kind of cover the topic in a little bit more detail or more specifically based on what you want to learn. Otherwise, my plan was to keep on going with particle astrophysics. So, it can seem a little bit haphazard what's happening during these live streams, but there is a method to this madness. Basically, we've covered a lot of the foundational sort of physics at a, higher level in the months of like October, November-ish timeline. And now, at this point, more recently, we've been covering cosmology because that's where we get the insights into the open questions of dark energy and dark matter. So we're basically covering like all of physics. And because we laid the foundation of quantum mechanics in previous discussions, now we've gone a little bit more into particle physics, which is a product of quantum mechanics. And also because I talked about astronomy and astrophysics, I have been now talking about particle astrophysics, which is also my own, topic. So, we can have these sorts of discussions where we cover some equations and some things like that, and we can also cover, keep on continuing the way we were gonna continue, which is that I will cover particle astro. The next bit that I will cover in particle astro is gonna be, let's see, we talked about Antarctica, and we talked about Cherenkov radiation, optical Cherenkov, radio Cherenkov, and then I was going to talk a little bit more about the instrumentation, I think, next. So that's where we'll pick up next time. And yeah. So thank you. Thank you, everybody. Thank you for being here. Thank you so much. And I will see you next time. I will take a shower. I might go live again tonight, actually. So I'll take a shower and I'll see you soon. Thank you so much for the